Yeah.
What do you say, Sean? Because you're buffered all, but don't mean you can down plays.
No, I guess all of them already signed.
No, we all always go eat at church on Sunday. I'm not gonna leave. We'll go eat. Because you haven't shown me the we go to Larry's. Put on. See, I gave more to the order.
Okay, so good morning everyone. So today we're going to continue our revision of things that we learned in structure analysis 1. So we had this example last time about drawing the bending moment diagram in a beam, okay? So we had this beam. To draw the bending moment diagram, we needed to calculate the moment at the key or the critical points. Those were point A, B, C, and D. So we calculated the moment at those 4 points, okay? That's what we did last time. So MA was equal to 0, MB was equal to negative 120, MC was positive 120, and MD was 0. So we plotted those 4 values, 0 here, negative 120, 120, and 0. And then what is left is connecting those points, either by curves or by straight line. You connect them by straight line if there is no loads between the points. So from point A to B, there is a uniform load. From B to C, there is a uniform load. From C to D, there is a uniform load. That means that it's all curves, okay? So we drew the curve from point A to B. Now we want to draw the curve from B to C and then the curve from C to D. To draw the curve, okay, the curve is always upwards as long as the load is downward, okay? Gravity load, okay? If the load is a gravity load, then the curve, the parabola is upwards, okay? So how to draw it? You connect the 2 points by a dotted line, okay? And then from the center of that dotted line, you add the parabola, okay? How much is the height of the parabola? For a uniformly distributed load, it's WL squared divided by 8. It's always like this for a uniformly distributed load. So W here is the intensity of the load, which is 10 kilonewtons per meter, multiplied by the length, which is 8 meters squared divided by 8. So that height is 80 kilonewtons meter. And then you draw the curve from the start here, passing through this extra point, and then third point here, okay? So that's the bending moment in this part. Now, the third part here, from point C to point D, again, there is a parabola. How to draw the parabola? You draw a dotted line. That's the reference for you, okay, to draw your parabola. So you're actually adding the parabola to this line. You're adding a parabola of what height? W L squared divided by 8. W is the intensity of the uniform load in that section, which is 20 kilonewtons per meter here. 20 kilonewtons per meter. L is the length, which is 10 meters here. So 20 multiplied by the length, which is 10 squared divided by 8. So this height is 250 kilonewtons meter. That means it's larger height like this. And then you go your parabola. So this is the bending moment diagram. You need the hatching. So actually this is the bending moment diagram from the solid curve to the line. Those dotted lines are just lines, okay, where you add the parabola to it, okay? So it's not, you know, it has nothing to do with the real bending moment, okay? Those dotted lines, it's just a reference line. You're adding, you have this line, and then you're adding on top of it this parabola. That starts from here to here. Here you have this line, you're adding this parabola to it, okay? So this is the bending moment diagram for this problem. Any question? Yes?
Is the top of the curve, what am I trying to say? Is the top of the curve always going to be at the top? Is in like...
It can, like for example, here this part is negative. You see the curve goes up, and then here this part is negative, this part is positive.
But it's never going to be at the bottom, right?
As long as, you know, you're talking about those parabolas.
Yeah.
As long as the load is a gravity load, it's going downward, yeah, the parabola is up, upwards, okay? Unless you have a uniformly distributed load that is applied upward on your structure, that can only happen usually like in the soil, okay? The reaction of the soil in your structure. So let's say you have a foundation that is resting on some soil here, okay? So in this case, the uniform load is acting upwards. In this case, the parabola is going to be downwards. That's the only case where the parabola is downwards. Okay?
That's just the case because that's the way we defined it, right?
Yeah, if you have a simple beam, you have the load, it's going to be a positive moment, not a negative moment. Okay? So, any question? Okay, great. Now let's take another example. We're still revising things that we learned in Structural Analysis 1. Okay? So another example here about things that we learned in Structural Analysis 1 that was at the end of the semester. Okay? Using the conjugate beam, the method of conjugate beam to calculate deflection. So in this example, we have this simple beam with those two loads applied on it. One load is 6 kilonewtons, the other load is 9 kilonewtons. This is point A, C, D, and B, and those dimensions here are 3 meters each. Okay? In this problem, we're required to find the deflection at point C and the rotation of the rotations at points A and B. Okay? So the method of conjugate beam is a method that is used, okay, to calculate the deformations, deflection or rotation at different points. Okay? So just a reminder, what was the method? What were the steps of this method? Okay? So the steps of the method of conjugate beam to find the deflection, okay, or the rotation at given points on a given beam using the method of conjugate beam, first you have to draw the bending moment diagram, exactly like we did in the previous example. Okay, so you start by drawing the bending moment diagram, and then, okay, you treat this bending moment diagram as a load applied on the conjugate beam. And then you draw the conjugate beam itself. The conjugate beam can look different from the actual beam. Draw the conjugate beam according to those rules. What are those rules? If in the real beam you have an end pinned roller support, okay, whether it's pinned or a roller support, but it's at the end of the beam, on the conjugate beam, it remains the same, pinned or roller, okay? In the real beam, if you have a fixed support in the conjugate beam, that becomes a free end. And opposite, if in the real beam you have a free end on the conjugate beam, that becomes a fixed support. Okay? If you have an internal pinned or roller support, okay, on the conjugate beam, that becomes an internal hinge. And the opposite, if you have an internal hinge in the real beam, okay, in the conjugate beam, that becomes a pinned support. Okay? And then, so now you have the real beam, you draw the bending moment for it, you take this bending moment and assume it's a load, okay, on the conjugate beam. You draw the conjugate beam according to those rules, okay? And then you solve or analyze this conjugate beam and find the deflection and the rotation. How to find the rotation or the slope, okay? Slope or rotation at any point is the shear at that point on the conjugate beam. And the deflection at any point is the moment. At that point, on the conjugate beam. Okay? So let's apply those steps now to solve this problem. We have this problem. We want to find the deflection at point C, the rotation at point A, the rotation at point B. So let's follow the steps. What are the steps? Draw the bending moment diagram. Okay? So let's start those steps. Let's follow those 4 steps here. So applying those steps, we want to draw the bending moment diagram, okay, for this beam. The beam looks like this. This load is 6 kilonewtons, and this load here is 9 kilonewtons. A, B, C, D. How to draw the bending moment diagram? We wrote the steps of drawing the bending moment diagram in the previous lecture. How to draw the bending moment diagram? You need to find the moment at the key or the critical points. What are the key or the critical points here? Any point that has a concentrated force. The start and the beginning of the beam, the start and the beginning of any distributed load. Okay? So what are those points here? Point A, B, C, and D. Point A and point B, there are concentrated force, the reactions. There are the reactions of point A and point B. And point C and point D, there are concentrated forces as well. So those 4 points are all critical points. I need to calculate the moment at those 4 points. And then we're going to connect them either by straight lines or by curves. Okay? So now, to calculate the bending moment diagram, okay? How much is the moment at point A? 0. How much is the moment at point B? 0. How much is the moment at point C? How to calculate the moment at a point? Take a section at that point. So I need to take a section at point C. Break my beam into 2 parts at point C. Part that is left of point C, part that is right of point C. And then study and write the equations of equilibrium of any of those 2 parts. Not the 2 of them, just one of them is enough, okay? So when you take a section at point C, which is easier? Should you study the left part or the right part? The left is easier. So when you study this part, the equilibrium of this part, you need to know how much is AY, right? So you need to calculate the reactions here. You need to find the reactions, how much is AY and BY. So to find the reactions, you apply the equations of equilibrium for the entire beam. Okay? So here, let's draw the free body diagram here. So here we have a force, reaction AY. Here we have a reaction BY, and we have a BX. BX is 0. From the summation of the forces in the x direction, there is no forces in the x direction other than Bx, so Bx is 0. Okay? So to find AY and BY, okay, let's take the summation of the moments at point A, okay? Sigma moments about point A equal to 0. We have 6. Let's assume anything rotating counterclockwise is positive. So we have 6 kilonewtons, okay, multiplied by this distance, 3 meters. So 6 times 3, and then plus 9 kilonewtons times its distance to point A. How much is that distance from A to D? 6 meters. And then minus BY multiplied by its distance to point A. How much is that distance? 9 meters, equal to 0. So from this, we can find BY. So BY is going to be equal to 8 kilonewtons. So now I know BY is 8 kilonewtons, and then I apply the summation of the forces in the y direction equal to 0. What are the forces in the y direction? We have AY. We have 6 kilonewtons downwards, so it's negative. 9 kilonewtons going downwards, so that's negative, and then plus 8 kilonewtons, which is BY, equal to 0. So from this, I can find how much is AY. So AY is 7 kilonewtons. So now I know how much are the reactions, okay? AY and BY. Now we can go ahead and find MC. How much is MC? You can take a section and find MC, but I'm just going to do it in my mind here. So MC, when you cut here, there will be the shear and the moment and the normal force taking moment about point C. MC is going to be AY times 3. Right? Any problem with that? You don't need to draw the free body diagram. If you draw the free body diagram of the section at point C, so this is point C, here you have AY, which is 7 kilonewtons. If you take the section, then this is VC, NC, and MC. So MC is going to be equal, if you take moment here, MC is going to be AY times this distance, which is 3. So MC is 7 kilonewtons times 3 meters. this distance here. So it's 21 kilonewtons meter. That's MC. What about MD? To find MD, you have to find the moment at point D. You take a section here, and then you either study the left or the right part. Which one is easy? The right, it has less forces. How much is MD then? It's 8 times 3, right? So MD is 8 times 3, so 8 kilonewtons times 3 meters. So this is 24 kilonewtons meter. How would you know the sign? If the moment is bending the beam upwards, then it's positive. So as you see here, AY is bending this moment about point C upwards, so that's positive. Here, BY is bending this beam about point B upwards, so MD is BY times 3, it's positive. Okay? So this is MCMD. So now we can draw the bending moment diagram. Or we're just trying to do the first step. We have MA is equal to 0, MB is equal to 0, MC is equal to 21. So here, I'm just going to plot 21 kilonewtons meter. And then MD is 24. So I'm just going to plot here 24 kilonewtons meter. Now I just plotted the 4 points, A, the moment at A, B, C, and D. This is the bending moment diagram? No, I have to connect those points together, okay? How would I connect them together? You just connect each two consecutive points, either by line, or by straight line, or by curve. How would you decide? Well, is the relationship is going to be linear or a curve, or a quadratic relationship? The loads from point A to point C. Are there any loads? You see here, there are no loads. There is no uniformly distributed loads or whatsoever from point A to point C. That means it's a linear relationship from A to C. So it's just a straight line. From C to D, again, there are no loads. So it's just a linear relationship. And then from C to B, again, there are no loads. So it's linear relationship. So this is the bending moment diagram. Okay? Now we do the bending moment diagram. What would you do with this bending moment diagram? Just follow the steps. Now we did the first step. We do the bending moment diagram. Treat this bending moment diagram as a load applied on the conjugate beam. Okay? Then draw the conjugate beam. We need to draw the conjugate beam. How to draw the conjugate beam? When you have a support that looks like this, it remains the same, right? That's the only thing that we have here. Our beam looks like this, okay? So the conjugate beam, so now this is the conjugate beam. On the left end, we have an end roller support, so that remains the same. At the right end, we have a pin support that remains the same. And then we have those loads. The bending moment is the load. Here, just to be more accurate about the steps here, okay? You have to divide this by EI, okay? If you remember this, you just have to divide this by EI. So the bending moment here, okay, was 21. The load is 21 divided by EI. Here it's 24 divided by EI. This is a load that is applied on that beam. Okay? This is a load that is applied on that beam. Okay? Now, if you have a beam with this type of applied load, what's this load? From here to here you have a triangular load. From here to here you have a trapezoidal load. Here you have a triangular load as well. Okay? Now, you need to solve this beam. You need to find the deflection or the slope. What's the slope at any point? The slope is the shear. So you need to find the shear at point A here and the shear at point B. Why? Because you were required to find the slope. So the slope is the shear. you were required to find the deflection at point C. What's the deflection? The deflection is the moment on the conjugate beam. So you need to calculate the moment at point C here on this conjugate beam, in this new beam. Okay? So to do this, you're going to need to find the reactions, AY and BY. Again, someone would say, I already know how much is AY and BY. I calculated them. There were 7 kilonewtons and 8 kilonewtons. No. Those were the reactions on the real beam. Okay? Now you need to find the reactions on the conjugate beam. It's a brand new beam. It's a different beam. It's the conjugate beam. It's not the real beam. So the reactions are not going to be the same. It's not the same beam. It's a new beam with different loads. Okay? So we need to go ahead and find the reactions here. Okay? So to find the reactions here, okay, so this is here. We're solving a new problem. It's the conjugate beam. We need to find the reactions on this conjugate beam. So to draw the free body diagram, here you have AY, here you have, AY is going to be downwards. Because if you remember from structure analysis 1, when you draw now the loads, you have to, put them in the opposite direction. And BY is going to be downwards as well. What do I mean by the opposite direction? This triangular load, how much I want to remove it and put an equivalent force. How much is the equivalent force? 1/2 the base times the height, right? And it's going to be acting upwards. That's for the conjugate beam. It's in the opposite direction. So 1/2 the base, okay, times the height. How much is the base, the length of the base? 3 meters. The height. How much is the height of the load? 21 divided by EI. So actually this is 31.5 kilonewtons meters square. So we have this load here with this concentrated force that is equivalent to that triangular load. Okay? And then for the trapezoidal load, okay, to work with this trapezoidal load, I'm just going to divide it into a rectangular load, okay, and a triangular load on top of it. Okay? How much is the equivalent force to that rectangular force? How much is that?
1/E times 3.
Okay, so the area of that rectangle is the base times the height, so you have 24 divided by EI times 3, which is equal to...
Wouldn't it be 21?
Yeah, 21, sorry. 21, okay, times 3, so that's 63 kilonewtons meter square. What about this purple load, the triangular load here? How much is this? How much would that be? 1/2 the base. How much is the length of the base? 3. How much is the height? 3 over EI. This is 21. This is 24. So I already took 21 here. So what's left here is just 24 minus 21. So this is 3. So that's 4.5 kilonewtons meters square. And then we're going to have this triangular load here. Okay? It's upwards, 1/2 the base, which is 3, times the height, which is 24. This is here divided by EI. Divided by EI. And here it's divided by EI and divided by EI. So 21 divided by EI, sorry, 24 divided by EI. So that's 36 divided by EI kilonewtons meters square. So now I have those four loads. 1, 2, 3 forces, okay, 4 concentrated forces. Applying this beam, I want to apply the equations of equilibrium to find AY and BY. Okay? So how would you find AY and BY? You take moment about point A, summation of the moments about point A equal to 0. Let's draw by colors here. The first Z force, how much is the moment of this force? It's the magnitude of the force, 31.5 divided by EI multiplied by its distance. How much is this distance here? 2 meters. This load is 1/3, 2/3 L and 1/3 L. Okay? The location of the centroid of the center of gravity of the triangle. Okay? So 2 meters. Plus, for that green force, the magnitude of the force is 63 divided by EI multiplied by its distance to point A. How much is the distance from this green force to point A? How much is this distance? 4.5. This distance here is 3. And this is 3, so 1/2 of it, this force is right in the middle of that segment CE. So this is 1.5 plus 3, so that's 4.5. So 4.5 meters. And then the purple one, the magnitude of the purple force is 4.5 divided by EI multiplied by its distance. How much is this distance? You have 3 here plus this distance. This is 2. This force is at 2/3 L. 2/3 3, so it's 2 plus 3, so that's 5 meters. And then plus the blue force here, the 36 divided by EI multiplied by its distance. How much is that distance? From point A. This is 3, this is 3, and then this is just 1/3 L. This is 2/3 L. L is 3 as well, so just 1, so that's 7. So this is 7 meters. And this distance here is 5 meters. This distance here is 4.5 meters. Okay? What else do we have? Are those all the forces? By. So negative by, because it's in the opposite direction, multiplied by its distance, which is how much? 9 meters. Everything is equal to 0. So from this equation, you can go ahead and find By. So By is going to be 69 divided by EI, kilonewtons meter square. Okay? 69 kilonewtons per meter square divided by EI. Okay? That's the slope. That's By. And then you take the summation of the forces in the y direction equal to 0. Okay? So what are the forces in the y direction? You have this red force, the 31.5 divided by EI. You have the green force, which is 63 divided by EI. You have the purple force, which is 4.5 divided by EI. You have this blue force, which is 36 divided by EI, and you have By, which is negative 69 divided by EI, and you have negative AY equal to 0. So from this equation, you can go ahead and find AY. So therefore, AY is equal to 66 kilonewtons meter square divided by EI. So the slope, how much is theta A, the slope at point A? How much is the slope at point A? the shear at point A? How much is the shear at point A? How to draw the shear force diagram? Do you remember this? How would you draw the shear force diagram? You start from the left and you go down with the forces and up with the forces. So at point A you have AY, which is 66 going downwards. And then you're going to have those loads. It's a triangular load, so that means that you're going to have a curve. And then at the end here, you're going to have BY going downward and it's going to end by 0. That means that this height here is equal to BY, which is 69 divided by EI. This is how your shear force diagram is going to look like, right? So the slope at point A is equal to the shear at point A. How much is the shear at point A? Negative 66 divided by EI, and it's unitless, okay? That's the slope at point A. What about theta B, the slope at point B? How much is the shear at point B? It's the reaction at point B, which is 69 divided by EI. So that's the slope at point B. Now we want to find the rotation, okay, at point C. The deflection at point C. Let's give this the notation U. The deflection, this is the deflection at point C, okay? The deflection at point C, okay? How to find the deflection at point C? It's the moment at point C. We want to find the moment at point C on the conjugate beam, not on the real beam, on the conjugate beam. How would you find the moment at point C? How to find the moment at any point? Take a section at that point, right? So I'm going to take a section here. Which part would you study, the left part or the right part of point C? Which is E, the left part. So taking moment at point C here, you're going to have AY times its distance, and then this force times its distance. Okay? So this is the section at point C. AY here was equal to 66 divided by EI, and we had this thread force, concentration of the triangular load, that was 31.5 divided by EI, and then here at point C that is VC, NC, and MC. Okay, so we would like to find MC. Why do we want to find MC? MC is the deflection. MC, the moment at point C on the conjugate beam, is the real deflection. Okay, so let's take moment here. How much is this distance? 3 meters. How much is this distance? 1 meter. 1 meter. So we have negative. So UC is negative 66 divided by EI times its distance. Why negative? Because it's bending the beam downwards. Okay. So negative 66 divided by EI times 3 meters plus 31.5 divided by EI times 1 meter. That's MC, the deflection. So that is equal to negative 166.5 divided by EI, and the unit is in meter. So that's the deflection at point C. Any question? Okay. We're going to need the method of conjugate beam to start our new chapter this semester, which is the slope deflection method, to prove many things, okay, that we're going to use, okay, right away in the slope deflection method. So you're not going to use the slope deflection method yourself, but we need the, sorry, you're not going to use, the conjugate beam method yourself, but we need the conjugate beam method to prove some formulas, some values that we're going to use in the slope deflection method, okay? So now this ends our revision, okay? And now we can start our semester, okay? Our new things, the slope deflection methods, okay? So what's the slope deflection method? It's a method that is used, okay, to find the internal forces, okay, and deformations in indeterminate beams. Can you use it to find the deformations or the deflections or the internal forces in a determinate beam? Yes, but it's going to be tedious, okay? For a determinate beam, it's easier to use the methods and the way that he used in structural analysis 1. Just use the equations of equilibrium. You don't need to use the slope deflection method to find the internal forces in a determinate beam. You can use it, but you really, it's going to be just more work that is not going to help you, okay? It's not going to give you any extra thing, okay? So here, so the slope deflection method is a deformation method used to calculate the internal forces in beams and frames generally. You can use it for determinate or indeterminate beams, okay? But it is more suitable for indeterminate beams, indeterminate structures. You cannot use it to solve trusses, okay? You can only use it for beams and frames. It's not suitable. You cannot use it for trusses, okay? So here, in this definition that we wrote, the slope deflection method is a deformation method, okay? What do we mean by deformation method, okay? So to solve indeterminate structures, okay, we have two, categories of methods, okay, that can be used to solve indeterminate structures. One is deformation methods, and one is force methods. What's the difference between those? When you have an indeterminate structure, okay, what is meant by indeterminate structure again is that the equations of equilibrium are not enough, okay, to find the internal forces and to solve that structure. You need more information, right? So where would you get those more informations, okay? So to get those more informations, you have a deformation method. The deformation methods, the more information that you find, okay, you find the deflection at certain points, and those deflections or rotations, deformations mainly, deformations are categorized into deflections and rotations. So you find, the deflection or the rotation at some points, and then from finding the deformation and the deformations at those points, you're going to be able to draw the internal force diagram. Okay? So in this problem, what you're looking for to solve and find the internal forces, you're actually not going to find that right away. You're going to first find the deformation at some points. Okay? Those are your unknowns now. The deformation at some points. And once you find those deformations, okay, there are some formulas that we're going to see. Okay? Actually, it's just one formula, okay, that transfer those deformations okay, into the internal forces. Okay? And that's why it's called the deformation method. You need to find the deformations to find the internal forces. Okay? The other method is the force method. For the force methods, okay, you need to find forces, unknown forces, to find the internal forces. Okay? So the slope deflection method is not a force method, it's a deformation method. Okay? You're not looking now for the unknowns to be forces. No, your unknowns are deformations. Okay? Once you find some deformations, that's it. You can deform or translate those deformations into the internal forces. Okay? So to do this, there is some foundation that we need to build. Okay? The first thing that we need to learn, okay, we're going to introduce a new term here called the fixed end moments. Okay? We're going to shorten this to be FEM. Okay? Fixed end moment. Okay? What is a fixed end moment? It's a new term that we're using now. If you have a beam element, there should be no supports there other than the end supports, okay? To say that this is an element, okay? If there is some support here, then this is an element, and here, this is another element, so two elements, okay? So we have an element here, okay? And there are some loads applied in this element. What type of load is this? I intentionally go with as any load, okay? You have some load applied to the beam, okay? Or that member, okay? If you assume, if this member is member AB, so the ends here are A and B. If you assume, they don't really have to be fixed, but if you assume that point A and B are fixed, okay? Then this member is simply a fixed beam. You have both ends fixed, okay? The reaction moments here, the moments for the, fixation of the beam are called the fixed end moments. So this is the fixed end moment at point A, and this is the fixed end moment at point B, okay? And to be more precise later on, this is the fixed end moment at point A, but it's on beam AB, so we're going to call it M fixed end moment AB. And this is here, we're going to call this fixed end moment BA. Because there might be another member, okay? Like, for example, if you have a beam that looks like this, okay? So this is A, B, C, D, okay? And there are some forces applied here. And I ask you, how much is the fixed end moment at point B, okay? If I ask you this question, what is the fixed end moment, you have to have a member, okay? So here you have to break this beam into different members, okay? So here we're going to have member AB and member BC and member CD, okay? On member AB, it's not fixed, but if I ask you how much is the fixed end moment, what you do is you assume that both ends are fixed, okay? And the fixation moments, the moments for the fixation here are called the fixed end moments. So this is the fixed end moment, AB, and fixed end moment, BA. For BC, the fixed end moments, you assume that both ends are fixed, and this is fixed end moment BC. You see now why we needed to write BA, not just B, because here this is, if I just say fixed end moment B, this is going to be fixed end moment B, and this is going to be fixed end moment B, but they are two different things, right? So I just, to put a notation that this is the fixed end moment at B, being AB, I just write BA, here I write BC, okay? And this is going to be the fixed end moment here. And CB, the fixed end moments on this part here, okay? is fixed end moment CD and fixed end moment of DC. Okay? So again, let's write now. What is the definition of a fixed end moment? The fixed end moment, okay? The fixed end moments are the moments, okay? Fixed end moments. So those are the moments at the ends of a beam element. Not the entire beam, each element, okay? At the beam element, fixed at both ends. What does fixed mean to you? A fixed support. What is a fixed support? It's a support where there is no rotation or deflection, right? So this is a very, very important thing here. I'm going to write it here. What do I mean by fixed end? Both ends are fixed. There are no deflections. No deflection or rotation at the ends. Okay? So let's see here. We want to find the value of the fixed end moments for different cases or for different types of loading. Okay? That's what we want to do now. Okay? How much is the fixed end moment for different type of loading? Okay? So we're going to start here with finding the fixed end moments for a concentrated force in the middle. So we have a beam element, not an entire beam, just a beam element of a length L. And that beam has a concentrated force of a magnitude P. P can be any value. It's just right in the middle of that beam. That means that this distance is L over 2. And here this point, let's name it A, B, and let's name the point in the middle, let's say C. We want to find the fixed end moments for this load. We have number AB. We want to find how much is the fixed end moments. So what does fixed end moment means? It means that point A is fixed and B is fixed. You have to fix them to find the fixed end moments. Okay? And now we want to find how much is those moments. So the thing is, to find those moments, you need to find the reactions. Draw the free body diagram and find the reactions, right? This is an indeterminate beam. If you count the number of reactions, you will find that they are actually more than the equations of equilibrium that you have. So if you try to use what you learned in structural analysis 1 to find the reactions MA and MB, AY and BY, you're not going to be able to do it. Why? Because you have 6 reactions, 3 here and 3 here. So those are 6 reactions, right? And you have only 3 equations of equilibrium. So it's impossible to solve for the reactions just using the equations of equilibrium. Someone would say, no, we don't have 6 unknowns. Why is that? If I draw the free body diagram, you might say, okay, this beam is symmetric, right? So that means that AY and BY should be what? Equal, right? And just 1/2 P. So I know, yeah, this is P over 2, and this is P over 2. And since the beam is symmetric, so here, if this fixed end moment, MA is the fixed end moment, right? This moment MB is simply equal to MA due to symmetry, right? So yes, that's right. But actually, to reach those, conclusions, you actually use your equations of equilibrium. Okay? You use your equations of equilibrium to reach those, conclusions. When you say sigma Fy equal to 0, so P is equal to AY plus BY, and then you take moment here, you're going to find that those are P over 2. That's it. You already used your equations of equilibrium to reach this, result. Now, how many unknowns do I have now? Just neglect AX and B and BX. We're not interested in knowing those. Okay? Just one unknown, MA, because MB is equal to MA here, right? So all I need to find is how much is MA. Okay? Let's name this M. Okay? M. Just this fixed M moment. But you already used all your equations of equilibrium. So how would I find M? This is the procedure that we're going to follow, okay, to find M. And that's why I started by revising the method of conjugate beams, okay? So what I'm going to do here, I'm going to use a concept that we introduced in structural analysis 1. That concept was the method of superposition, okay? So here, in this beam, okay, this is the beam. This is the free body diagram of our beam, right? I'm going to break it into two different beams. Okay? So this beam is equivalent. I'm just going to have P here along with P over 2 and P over 2. This is actually a single beam, right? Just forces. There are no moments and moments. Plus, so this is, let's say, beam 1 plus this moment and this moment. When I break my beam into two different beams, each of them has to be in equilibrium. Okay? This beam is in equilibrium, and this beam also is in equilibrium. Okay? So if you add this loading and this loading, you just have everything here. Okay? Now, I would like to draw the bending moment diagram for this beam. How to draw the bending moment diagram for this beam? The moment at the critical points, right? Or I can draw the bending moment diagram for this beam and draw the bending moment diagram for this beam and add them together. That's the method of superposition. Okay? So that's what I'm going to do now. I'm going to draw the bending moment for beam 1 and draw the bending moment diagram for beam 2 and add them together. So to draw, this is point A, B, C. To draw the bending moment diagram for beam 1. This is the bending moment diagram for beam 1. How to draw the bending moment diagram for beam 1? You take the moment at the critical points. What are the critical points? A, B, and C. Okay? How much is the moment at point A? 0. How much is the moment at point B? How much is the moment at point C? This force. You take a section here, and then you study this part. So it's P over 2 times L over 2. So it's PL divided by 4. Okay? So the bending moment here, 0 here, 0 here, just right in the middle, it's PL divided by 4. And this is positive. This is the bending moment diagram for beam 1. Okay? Let me use a different color here and draw the bending moment diagram for beam 2 or loading 2. Okay? How would you draw the bending moment diagram for this beam? Just find the moment at the critical points. What are the critical points here? A and B. How much is M8? How much is the moment at this point? Take section at this point. You need to study the left part or the right part. Which one is easier? Same. If you study the right part, the left part, it's M. If you study this part, it's M. But it's negative because it's bending the moment, the beam up, right? So negative M. How much is the moment here? Negative M as well, right? Any confusion here? Okay. So the bending moment diagram for beam 2, here you have negative M, and here you have negative M. And then how do you connect those 2 points? Are there any loading here from point A to point B? Some would say, yeah, there is this force. No, this force is on beam 1. On beam 2, from here to here, there is nothing. You just connect those 2 critical points, those 2 key points, by straight line. But that is negative, okay? That's the bending moment diagram for beam 1 and beam 2. What do I need to do with those 2 bending moment diagrams? I need to add them together, okay? To find the total bending moment diagram for the entire beam. How would you add them together? Okay? This is how I'm going to add them together. Simply, I'm just going to put them on top of each other. So here, this is M and M. This is the bending moment for beam 2, right? And the bending moment for beam 1 was positive. So that's the x-axis. You have this part is negative, this part is positive. Right? Actually, if you want to draw it in a better way, here the summation of the moment from this line and this line is negative M. It's negative M. Here you have negative M plus PL over 4, so it should have been like this. Right? You should have subtracted this triangle from this reference line. Understand what I'm saying here? So mainly this is the equivalent. It's negative M, this is a dotted line, and then actually I'm adding here, or subtracting from this M, PL over 4. That means that this point here, it's PL over 4 minus M. This is M. If you're going to do the hatching, this is how it should look like. This is negative here and positive here. You understand what I'm doing? Okay? But I didn't, I just kept each one of them separately. Okay? That's going to be easier to what we're going to do now. Okay? But this is actually the final one. Okay? You have this negative part, and you add this positive to it. So it becomes like this. Okay? But this is the one that I'm going to use now. So now, what I did it answer the question that we're looking for? How much is that moment M? Did we find how much is M? No. We still didn't find how much is M. Okay? So how will I find M? So the way I'm going to do this, okay, I'm going to use a piece of information that I know. What is that? What's that piece of information? Can anyone know this? It's related to the conjugate beam, our discussion of the conjugate beam. Do you know any information that would help you to find M? That I know that this is a fixed beam, right? By definition, you're trying to find a fixed M moment, so you're fixing A and B. So the deflection and the rotation at both point A and B are zero. I actually have 4 pieces of information that I can use. The deflection at A is equal to 0. The deflection at B is equal to 0. the rotation at A is equal to 0. The rotation at B is equal to 0. I know those information, right? So I don't need all those 4 pieces of information. I just need one of them, because I only need to know how much is m, the moment m, right? So now, if I would like to find the deflection at point A, how can I find the deflection at point A? How would you find the deflection at any point on a beam? Use the method of conjugate beam, right? So how to use the method of conjugate beam?
Make it a free end.
Draw the free body, draw the bending moment diagram for that beam, right? We already did this, right? We already drew the bending moment diagram. This is the bending moment diagram, right? And then put this bending moment diagram, assume it's a load, right? And put it on the conjugate beam. How would the conjugate beam look like? This is the original beam. How would the conjugate beam look like?
The free end.
Both ends are free. This is fixed on the real beam, so on the conjugate beam it's going to be a phi end. This is fixed on the real beam, so on the conjugate beam it's going to be a phi end, right? So now, this is our conjugate beam. Let's go here. The conjugate beam, and just draw, put the bending moment, it's PL over 4 here, and M here. This part is positive, and this part is negative. So you actually have two loads applied on this beam. One that is negative and one that is positive. Okay? And this is your conjugate beam. What type of beam is this? It doesn't have any supports. That's fine. Okay? That's fine. This is how your conjugate beam look like. But even if it doesn't have any supports, this beam is in equilibrium. Okay? This beam is in equilibrium. What does equilibrium mean to you? Equilibrium means that the summation of the forces in the y direction is equal to 0. The summation of the forces in the x direction is equal to 0. The summation of the moments about any point is equal to 0. Right? So let's apply the equations of equilibrium. What's the equations of equilibrium? Sigma Fy equal to 0. That's one of the equations. What are the forces here? You have two distributed loads, right? One that is rectangular and one that is triangular, right? I want to remove this rectangular load. How much would that be? Let's see here. This is going to be downwards here. How much is that one? For the rectangular load, the equivalent rectangular load. ML, base times the height. And just don't forget to divide by EI. Okay? So ML divided by EI. What about that triangular load? I just want to remove this triangular load and put an equivalent force. Where would that equivalent force be? It's a symmetric triangle. So where's the centroid of that triangle? Right in the middle here. How much is the magnitude of that load then? That force? 1/2 the base. How much is the base? L times the height. How much is the height? PL over 4 EI. So here we have P L squared divided by 8 EI. Right? Now I'm just going to apply the equations of equilibrium. Apply the equations of equilibrium to the conjugate beam. the summation of the forces in the y direction should be equal to 0. What are the forces in the y direction? You have two forces, right? How much is the magnitude of those two forces? PL squared divided by 8EI and negative ML divided by EI. The summation of those two forces should be 0, right? The EI here cancels with the EI here. This L cancels with the square here. So, and then move M to the other side of the equation. So M, how much would M be? P L over 8. What's this? This is the fixed end moments that you were looking for. So for this B, if you have a member with just a concentrated force of a magnitude P, right in the middle of the length of that member L, you need those moments for the fixation of it, to make it fixed, okay? How much is those moments? PL divided by 8. Okay? Those are the fixed end moments. And what are their direction? When I solved, it was positive. What does positive mean? That my assumption here was correct. The fixed end moments are in this direction. Okay? They are negative moments, actually. Those are negative moments. So, that means here, therefore, for a concentrated force in the middle, the fixed end moments are equal to PL over 8. They are equal to each other. So here, this is P, this is L over 2, and those fixed end moments, this fixed end moment AB is PL over 8, and this fixed end moment of BA is PL over 8 as well. They are equal in magnitude, but they are opposite in direction. Okay? That's the first thing that we were able to find today. Okay? That for a member that is fixed from both ends, with just one concentrated force in the middle, the value of the fixed end moments are PL over 8. Do you need to do this derivation? No. We just did this derivation to reach this result. We're going to use this result later on, okay? Directly. You don't need to do this each time. Do you need to memorize those values of the fixed end moments? I guess, I would advise you just to memorize for a concentrated force right in the middle, okay? But even if you don't do this, it's right at the back of your book. Does anyone have the book? Okay. So here, just right in the back of the book, okay? You have here the table for the fixed end moments. Okay? Let me show you this here. So this is the back of your book, the fixed end moments. This is what we derived today. Okay? A member with just a concentrated force right in the middle of the length. L is the length of the member. You find that the fixed end moment here is equal to the same magnitude as the fixed end moment here. It's PL over 8, and you're given the direction here of those fixed end moments. Okay? If you don't want to memorize it, it's given here. Okay? On the test, I will give it to you if you didn't memorize it. Okay? As you see here, for different loadings, okay, there are different fixed end moments. In next lecture, we're going to derive some of those values here. Okay, we're going to derive this one, and we're going to derive this one, but we're not going to derive all of them. Okay, you just know how. You're just going to learn how we derive them, and then those are the values. Okay, if you follow the same steps for each of those cases. Okay, so that's what we're going to do next time. This is just some information that we're going to need to use the slope deflection method. Okay? Any questions? Okay, so thank you and see you next time.